Alright, so today I want to explain this Nurip's paper in 2020 with the title Denoising Diffusion Probabilistic Models. This paper by UC Berkeley. We present high-quality image synthesis results using diffusion probabilistic models, a class of latent variable models inspired by considerations from non-equilibrium thermodynamics. Our best results are obtained by training on a weighted variational bound designed according to a novel connection between diffusion probabilistic models and denoising score matching with Langevin dynamics. I have a playlist about score matching that I talk about all variants of score matching, such as denoising score matching. Score matching, the idea is that instead of learning, it doesn't have any explicit likelihood. You just try to maximize to learn the gradient of the probability distribution, not just probability, because the gradient of P is easier. So we call it the score matching. And of course, if you just the denoising version of that, it has better performance. And this idea of score matching is also related to diffusion. So as unlike variational autoencoder, variational graph autoencoder, which have explicit likelihood, in score matching we don't have any explicit likelihood. Everything is implicit. And Langevin dynamics and Monte Carlo, these are good for sampling. Once you have a good score, then you can just use SDE to do sampling. So this paper presents progress in diffusion probabilistic models. You see, they have done it for images, which is much easier because it's continuous, but in discrete problems like tabular data, language, and graph, it's much harder. Because even the gradient is not well defined, you should define the derivative. What is derivative in the discrete domain? And so this is a background for diffusion. What is the reverse process? What is the forward process? So Q, the posterior, we call forward process or diffusion process. Most people fix the forward, but some people learn even the forward. And we always learn the backward. We always learn the reverse process. So training is just by variational bound, this negative elbow, variational bound, negative likelihood. The forward process variances beta C can be learned by reparametrization or held constant as per hyperparameters. So efficient training is therefore possible by optimizing random terms of L. So it uses KL divergence to directly compare this P theta against the forward posterior. Because they are tractable when we condition on x0, they are tractable. So you see explicitly, you can derive it very easily. So we ignore the fact that the forward process variances are learnable by reparametrization and instead fix them to constants. And about the reverse, now we discuss our choices of our reverse process. This mean, mu, and variance, sigma. First, we set it to something like this, to untrained time-dependent constants. So experimentally, the first choice is optimal for x0 when you draw from the normal distribution. and the second is optimal for x0 deterministically set to 1 point. So to represent mu, because here you need to model the mu for the reverse process experimentally, to represent the mean, we propose the second parametrization motivated by the following analysis, that we can write L like this. We can have this parametrization. But C is just a constant that does not depend on theta. So we see the most straightforward parametrization of mu is a model that predicts mu, the forward process. However, we can expand this equation H and apply the forward process posterior. So we can rewrite it like this. So it's just expectation of this term over epsilon and x0. Where epsilon comes is just you have this parametrization. Whenever we have a problem in sampling, we just make it productive parametrization trick of variation autoencoder, if you remember. So it's very useful if you write this. So we have written our data related to this epsilon, which we draw from normal distribution. Now this epsilon appears. Then this equation 10 reveals that mu theta must predict this given xt, and since x sub t is available as input to the model, we may choose the parametrization. So epsilon theta is a function approximator. There's a function approximator intended to predict epsilon from xt. So algorithm 2 resembles the Langevin dynamics. This looks like the score. So you draw samples from that. So we can simplify it as this expectation, which resembles denoising score matching. Looks like denoising score matching over multiple noise levels, noise scales, indexed by T. So different noise levels, we have different, because epsilon is related to T as well. And equation 12 is equal to the variational bound for Langevin-like reverse process. And we see the optimizing an objective resembling denoising score matching is equivalent to using variational inference to fit the finite time marginal of a sampling chain resembling Langevin dynamics. So we assume image data consists of these, and we scale it to -1 and 1. So to obtain this log likelihood, we set the last term of the reverse process to an independent discrete decoder derived from the normal distribution. The main part of this paper is this. Very simple. Simplified training objective. With the reverse process and decoder defined, the variational bound consists of terms derived from equation 12 and 13, using this and this. So it's clearly differentiable with respect to theta. However, we found that it is beneficial. So they say that it is beneficial to sample quality to train on the following way. So instead of data, we go to the noise level. We want to the expectation is over epsilon. So T is equal to 1 corresponds to L0, with the integral in the discrete decoder definition approximated by the Gaussian probability density function times the bin width, ignoring sigma 1 squared and edge effects. So they did experiments with the use of, they use UNet as a backbone, similar to unmasked pixel CNN++. So here they send X0, and then here they receive it. We find that training our models on the true variational bound yields better code length than training on the simplified objective. But the latter, which they mean the variation, their simplified approach, has the best sample quality. Then they talk about progressive lossy compression, progressive generation, connection to autoregressive decoding, so we can interpret that Gaussian diffusion as a kind of autoregressive with a generalized bit ordering that cannot be expressed by reordering data coordinates. And this is the interpolations of these images with 500 time steps of diffusion. 500. So we have this source, pixel space interpolation, and the X prime. So this is the diffusion source. We can interpolate source images in latent space using Q as a stochastic encoder. In graphs, we don't do interpolation of two graphs. For example, when we have adjacency here, what does it mean to have interpolation between them? Maybe if we work on graphome, then because it's continuous and for dense graph, everything is obvious. But for a sparse graph, it's a challenge. So when we go from continuous domain to discrete domain, so discrete methods for generative modeling, like discrete score matching, is really hard. There are many papers on that, but they haven't implemented actually on graphs like QM9 dataset, Zinc dataset. They haven't done that. And in the appendix, they show the derivations, how they derive this. It's very simple to follow. Finally, they drive this KL divergence between forward and backward. And you have, of course, to find interpolations.